Indeterminate forms, what are they? Let's find out. Starting off with an example, here's maybe the simplest example I can think of. Let's look at f of x equals x over x. So this function is nothing but a straight line with a hole in it at the origin. So its limit, or if you've just watched the video on continuity, then you know that this is a straight line with a removable discontinuity at the origin. So this limit is definitely going to be equal to 1. No problem. But what if you tried to calculate this limit by incorrectly applying the limit laws? So what if you tried to calculate this limit by plugging in? So if you did that, then you'd say, well, it's going to be 0 over 0. And that's not so good. The reason why I say that's an incorrect application of the limit law is because you can only apply that quotient limit law when the denominator is not equal to 0, precisely to avoid things like that. But you might say, well, okay, let's just call 0 over 0 1 and be done with it. But there's a problem, because what if I looked at a new function? What if I looked at g of x equals x squared over x? And so what if I took the limit as x goes to 0 of g of x? And what can I do with this? Well, if you try to plug it in, you'll get 0 squared over 0, which is, of course, just equal to 0 over 0. And you might try to trick yourself and say, well, maybe this is still going to be 1. What is this limit, by the way? Let me show you how to figure this out with the limit laws. So let's actually start again. And if I have x squared over x, nothing stops me from rewriting that as x times x over x. And now here's a limit law that I actually can use, because if I know that limit of x over x as x goes to 0 is equal to 1, and we do know that because that's just the horizontal line with the hole in it, then the product limit law says that this has to be the product of the limits. So this limit as x goes to 0 of x is just going to be equal to 0. And this limit of x over x as x goes to 0 is equal to 1. You multiply them together, the answer is 0. So in other words, here's two different situations where you get 0 over 0 if you just try to plug it in. However, both those limits do exist, and they have different answers. This limit is 1, that limit's 0. But the issue is that we can't determine the answer. We can't determine the limit just by knowing that we have 0 over 0. And so when this happens, we call it an indeterminate form. So whenever it's true that plugging in just gives you an expression where you cannot determine the limit, that's called an indeterminate form. So we've seen 0 over 0, but there's other ones too. There could be a plus or minus infinity over plus or minus infinity. You're not going to be able to tell the value of the limit from that. The limit may or may not exist, who knows? And if it does exist, you don't know what the number is going to be. You could also have infinity times 0. You could also have infinity minus infinity. And in any one of those cases, we call those indeterminate forms because of the fact that we can't determine the value of the limit just by plugging in. Now there are some cases where we can determine things. So if I had something like, let's see, maybe let's look at f of x equals to x minus 2 over x. And say you wanted to look at the limit of f of x as x goes to 0. When you just plug in, you're going to end up with minus 2 over 0, right? If you just plugged in the number, then you'd get that expression, which we know is not a mathematical expression, doesn't mean anything. Is this an indeterminate form? No, because you actually can determine what happens to this limit as x goes to 0. So in fact, if I take the limit as x goes to 0, x minus 2 over x, well, what's going to happen? Whenever I see a constant over 0, I'm thinking plus infinity or minus infinity. And in fact, if you look at the graph of this function, that's exactly what you're going to see. You're going to see that when x is positive, then this expression is going to be like a negative number over a positive number. It's going to be going to negative infinity. You're going to be seeing that when x is negative, you're going to get a negative number on the bottom and a negative number on top. Those two negatives are going to give you a positive. So in that case, you're going to be going to plus infinity. So when you draw the graph of this function, schematically, it's going to look something like this. It's going to have a vertical asymptote at x equals 0. It's actually going to be negative when x is positive and positive. Positive when x is negative. So in fact, just from looking at this form, I can determine that there are two one-sided limits here, a negative infinity for values bigger than 0, and positive infinity for values less than 0. So this is actually not an indeterminate form. I can determine that the limit doesn't exist, and I can determine the way that it doesn't exist, the fact that we're escaping to positive infinity or negative infinity. But for the other cases that I mentioned, they are indeterminate. So let me give you a couple other examples. Let's pick an example. Let's look at tangent of x over secant of x. And for this one, where do I want to take the limit? Let's do limit as x goes to pi over 2. Now, if you just plug in pi over 2, well, if you look at the graph of tangent, it's got those vertical asymptotes at negative pi over 2 and pi over 2. So when you plug in pi over 2 to tangent, you're going to get infinity. And if you look at secant, remember secant is 1 over cosine. And cosine of pi over 2 is equal to 0. So secant would be 1 over 0, that's infinity. So if you just plug in the value x equals pi over 2, you're going to get an indeterminate form of the type infinity over infinity. And to be a little bit more precise, secant will have two of those one-sided limits. You know, one of them will be plus infinity if you're coming from the right, negative infinity if you're going from the left. But schematically, we'll still call that infinity over infinity. So here I cannot determine whether or not this limit exists just from trying to plug in. So what can I do? What I want to do here is try to simplify the algebra a little bit. So in fact, let's substitute these trig functions with what they're equal to. Let's take the limit as x goes to pi over 2. And I know that tangent is sine of x over cosine of x. And I know that secant of x is 1 over cosine. So 1 over secant of x. I'll go ahead and write it here. It's 1 over cosine. And that improper fraction reduces to my marker's on its last leg. The improper fraction reduces to cosine. So what we get is sine over cosine. Bear with me, I'm getting some more ink. Times cosine of x. And then you can see these cosines will cancel with each other, and we're just going to be taking the limit as x goes to pi over 2 of sine of x. And that I can figure out just by plugging in. And so what's sine of pi over 2? Sine of pi over 2 is equal to 1. Getting a little bit more ink there. And how can I just plug in? This is the same as the statement that sine of x is a continuous function. So because it's continuous, you can just plug in the value, and then you just have to remember that sine of pi over 2 is equal to 1. So here's an example of an indeterminate form of the type infinity over infinity. And generally speaking, if you have something like that, the limit might exist or it might not exist, you don't know. But in this case, after some further simplification, we did see that the limit did exist and was equal to 1.